I was supposed to say a couple words opening the conference. So it's been, this is the picture I taken yesterday. And that's the view. The little red house is the SIM building on the very right little building. If you go up for a hike, you see that building, our building here. I see there's a very good crowd, and the organizers has arranged a very good time, the autumn. I like autumn here. It's up very cold, and here we in the beautiful weather, in a good environment, and with very good crowd. I think everybody have, most people come here in the afternoon already had a hike. So, and that's very excited to see the new facility here, and the organizers want to thank the SIM and for the financial support and the other organization. And Erica is going to organize a walk, and she needs some help. Somebody, if you know somebody here, if you know the area, just let her know and co-organize the walk. Anything else I should be saying? I guess that's about it. So it's wonderful to come back here. I guess if you've been here lots of time, some people been here for coming here for 20 years, so you know everything about it. And you excited. I come here intermittently. I'm really very happy to be here too. And if you're new and then you follow everybody else, it's a great place to chat, to discuss, and to have a hike, a very healthy mix. So now I think I go to my talk. Okay. So I'm going to talk about the stochastic wave equation with very rough Gaussian noise. So I start with maybe something everybody knows. The space is going to be on the torus, two-dimensional torus. In that case, so the white noise would be on each frame mode, there's a Gaussian noise, beta n, or beta nt, so it's sort of Brownian motion. They are independent, except when the n is, if there's a pair, n and minus n, then the pairings will be conjugate each other. Otherwise, it's all independent Gaussian noise. So white noise in space is a distribution in space. Here, spatial regularity is -1 minus epsilon. And if you're in the parabolic setting, -1 minus epsilon plus 2 regularity, that's no problem here. Here, that would be a problem in the wave equation setting. Now, I asked ChatGPT to give me this picture of some time frame. It gave me some spatial fluctuations. Okay, it told me that it has used slightly color, very, very little color, otherwise it can't draw it, which is very honest. Okay, now rough space-time Gaussian noise. And so what we let delta to be the Laplacian. Does it show? Oh, good. So the Laplacian on the torus. And as usual, this Japanese bracket of lambda will be square root 1 minus Laplacian, because on the torus, the Laplacian has a lowest eigenvalue 0. We shift by 1, so everything is good. Now, n are the n square are the sort of eigenvalues. So the Japanese bracket n corresponding to those values, 1 plus modular n square. Now, the noise we do is we take the white noise, hit it by this fractional operator, lambda to the alpha. By that, we mean is a free mode at n is defined by multiply the free mode for the original distribution at n by n to the alpha, right? So it's smooth. The distribution is smoother if you divide it by n, so it decays at infinity. But now we multiply by n to the power alpha. Alpha is positive, so make it rougher. So that's a rougher noise. And this has regularities therefore -1 minus alpha. We hate it by derivative to the power alpha. And if we compute its correlation between x minus y is homogeneous in distance, is given by this in the free mode is given by n to the 2 alpha. In the real mode, we do a free transform back. Yeah. So that's the noise we're going to take. The equation we're interested in is wave equation, second order derivative in time. 1 minus Laplacian, I put it here, which is the same as the lambda square to rhyme with the Gaussian noise here. And we take a cubic nonlinearity. So, well, cubic nonlinearity models self-interaction of a certain order. Now, the Gaussian noise, well, just to model highly oscillatory, turbulent, and rough forcing. Now, I'll start with the linear wave equation, go step by step to where we get to. Suppose we take the linear wave equation with starting point u0, u1, and the solution is given by the linear propagator, which I call the ST, and that's the cosine t lambda to u0. This is just as before, this is a Fourier multiplier. This operator applied to u0 just means the Fourier mode at n is cosine t, replace this by n, and u0. So u0 hat of n, sum over this, multiply the EINX, right, the basis. So that's what this function is. And for u1, we take sine t lambda divided by lambda. So they all defined the same way by Fourier multiplier. If you look at this solution, we see that we started from initial condition, normally u0 in HS, sublib space of order S, u1 would be in HS minus 1. And we'll see that the solution at all t would belong to the same space as the initial condition. Just interrupt me if it's not clear anywhere. And so now we look at a determinist wave equation with nonlinearity, u to the k. Now this, the regularity, the well-posedness of this solution is actually reasonably recent endeavor. And we know that there's a critical value. The critical value depends on the dimension and the nonlinearity. It's locally well-posed in HS. And so HS is the initial condition, U0. So it's locally well-posed if your initial condition starting from HS for S greater than a critical value, SC of kappa. The two values, the criticality comes from a scaling criticality. Doesn't quite show, right? Okay. Sorry, none of them really shows. Yeah, there's a scaling criticality there, and there's a conformal criticality, and we take a maximum for that one, and this is a result by Linda Blau, Sog, 96, and Christa Colin de Tau in 2003. So for cubic nonlinearity, as we show here, in dimension 2, the critical value is 1/4. So it means the initial condition can be just below 1/4 for it to be well posed. It is actually ill-posed below it by a result of Michael Chris, James Collinger. Now, the wave, that's one feature of this cubic nonlinearity. In determinist case, you really have a stress value, threshold for the critical value. Also, it's local well-posedness result in general. We have local well-posedness, you could have blow up or shocks develops. And so this is all standard. There's a textbook examples, Reid and John. More recent result by Paul Liu Cho, and they studied stochastic wave equation with color in space wet noise. They show the blow up as a blow up or moment blow up for regular solutions. So in general, we don't expect a global solution. Now, how does one go about it? One typically looking for a space for the solution to exist where one can kind of develop a contraction principle on that space. And so the okay, that's why it doesn't work. Okay. But I don't have a pointer anyway, sorry. So the typical space one work with is called Bourgain space or Wave-Sobolev space. And it's called Bourgain space, but Kleinemann and Machadon, they have a very nice paper. It's also worked a long time ago. And they use this space as well, where they call the Wave-Sobolev space. Well, so the Wave-Sobolev space has interaction between time, the propagation time, and the spatial time. So the famous Bourgain space, which I write down as X with two parameters, S and B, so X as B space. S is for the spatial Sobolev, the Fourier transform. B is for the time transform. Now, so in this definition of the norm, thank you. So then you see, it doesn't work, but anyway. Okay, and so there I don't have pointer, but that's okay. Ah, yes, working. Now, so you see there's NS, the Japanese bracket N. If you take B equal to 0, that means I'm taking the Sobolev space in space of order S. And then we take the L2 norm in the Fourier transform, that's lambda in time. So if you take B equal to 0, that's L2 of the Sobolev space in X. So otherwise, you see the interaction between the time lambda and the n frequency coming in raised to the power B. There is some nice embedding theorem. It says LQ in time, LR in space is nicely embedded in SB if QR is wave admissible with respect to S, which means satisfy these two conditions. Okay? Now, also, they have the same property as Sobolev space. If you increase one parameter in S, and that's embedded, if you increase the parameter in B, that's also embedded. So that's a very nice space, but it's kind of difficult to work with. Okay, so now I introduce that space. Now we look at the Duhamel operator, which is the inverse operator, this wave d2t plus 1 minus delta. So this is called the Duhamel operator. So now we look at the linear operator. We're looking at the linear operator with the right-hand side. So inhomogeneous linear equation. And then the Duhamel operator would apply to a function in the following way. You take the g as x, and you multiply by the free multiplier sine t minus s with Japanese bracket lambda divided by lambda, and integrate it out in time. Now, it's quite a, I see something. So, no, what is really good is, this is very important. If you have a function, apply Duhamel operator, then look at the norm in SB, and you see you're gaining something. You start from S minus 1, and you could start from B minus 1 of the function, and you get to SB, okay? But the B could be not B minus 1, you could be a little bit less than B minus 1, that give us a factor of increase in time, allowing contraction argument to work. So this is a principle. Duhamel operator increase regularity by 1. So from S1 minus 1 to S, but it also increase a little bit in B, okay? For B minus 1 to B. And there's some standard text by Reed and Tao, and also some people recently in our community working on this also have a nice text on it. Now, for us, we have a regularity challenge involving the nonlinearity and the U cube. We know that the correlation function for the Gaussian noise determines the best regularity class to which it belongs to almost surely. We've seen the correlation functions summation n to the 2 alpha e a nx. And so that dictates your regularity class minus 1 minus alpha. So expect the solution at the best is C minus alpha. And so U3 is not defined. We all know that. Actually, we can do better than power counting. That's the point. Because there's non-linear interaction, there's some cancellations of signs in the procedure. We can do better than the sort of naive power counting, that is how you define a product function by taking, if one of them is positive, you expect the worst regularity. So, but we do a bit better, we'll see that. Okay, so that's my collaborator is Xianfeng Ren. He's a PhD student currently at Imperial College. So the main result is that now we have a local well-posedeness solution theory, which will remain, the solution will retain both nonlinearity and noise for alpha smaller than 3/8. Now, the object, as we said, is we want a good solution theory for this. And what has been done before? We know there has been a lot of work on stochastic wave equations recently. Probably one of the most significant work is Gubinelli Koch in 2018. They showed for white noise, and the Duhamel operator, well, in this case, the Duhamel operator just goes below 0 in regularity. And so they proved the well-posedness for the white noise case. This case is a little bit different from us because you see, the Duhamel operator is minus epsilon. You take any power of that, it's still minus epsilon. So essentially, the object itself, the powers and the cubic, and they actually did all nonlinearities. So they all belong to the same space. They can work on that. That's maybe one of the pioneer works. Now, recently, O and Okamoto is more recently, 21. They showed that if you have quadratic nonlinearity, there is a local well-posed solution theorem for alpha between 0.5. Okay. Now, where we come in is where we have a cubic. We can prove for alpha between 0 and 3/8. Okay, so what are we talking about solution theory? We are obviously in the territory of a singular SPDE. So the now classical wisdom is looking for a solution of the form of Pussy and plus V. Pussy is something rough, it retains the roughness of the noise. V is solving an equation with the correct nonlinearity, but it's a bit more regular. Okay? So we're looking for a sum of two different regularities, and you hope there's a uniqueness within this class and is well posed. There's existence as well. Now, this type of argument, well, if you have an inhomogeneous equation, we typically write down the linear solution, then use so a little bit evolution, then we take on the inhomogeneous case. And this has been used to solve equations, right? So you split your equation in two parts. One's linear with rough noise, the other one is nonlinear, called the remainder term. This for determinist wave equation is implemented in Bougon 96, actually by McKean 95, and he mentioned about that. Well, in parabolic SPD, we've seen a lot of that. We have Arnold sitting at the very end. Okay, and for stochastic wave equations, this implemented this strategy by the GKO 18 paper. And then also by Okamoto O Ptolemy with hard tree nonlinearity and quadratic case, and Deng, Naho, Yu, Bringham, O. Well, O1 Gina was the recent one. They look at the cubic, but for more regular than white noise case. Okay, so let's introduce this concept again. Suppose we use Cn denote Fourier truncation. So you take a projection of a distribution to the modes, the modular n, less equal to capital N. Then we want to solve the equation with a regularized noise. Then by the determinist theory, we talk about in Sobolev space h to a quarter plus, and we speculate to have a solution. Okay? Now, what in our case, we're going to see this is not possible. We need a renormalization. But in fact, the renormalization is not just useful, try to make the theory to work. It has been pointed out in the paper of Bavario, Haber, and Russo that even the very regular case, regular noise, if you take a Cn, then take the truncation to infinity, you may have a limit. You are in the case that there is a limit without renormalization. But the problem is when you do this, they have an example of limit equation become totally linear. The nonlinearity disappears. So that's called the phenomenon of triviality. There are also examples, the stochastic term disappear, all the solutions are totally constant. So this phenomenon of triviality exists. So renormalization appears to be useful, not just because it's non-regular, also because totally too, not because it's too rough, also because regularization tends to sometimes give us the noise, lose feature we don't like. For the moment, I see the feature you have a rough part plus nonlinear part of the solution. Looking for solution that form would actually ensure we do not have a phenomena of non-triviality. Now, let's look at the stochastic linear wave equation with the noise, linear without a cubic nonlinearity. In this case, we would have the Duhamel operator. That's this free mode applies to the noise. The noise is summation En beta n. So we apply that to every mode and truncate it to capital N. And so that's the Duhamel operator. We call that's the lollipop, right? And then anybody sitting here knows how to compute the modular square. I take, and that by Ito isometry, we get the order capital N to the 2 alpha, and alpha is positive, that blows up. So that means we're going to use a weak renormalization, remove the blowing up variance, and call this the cherry. So it is this is a result coming from O and Tokoma. Is the following. They essentially wanted, they're looking at cubic nonlinearity, they look at the cherry term. But let's also look at the lollipop. The lollipop belongs to a space with minus alpha regularity, a little bit below minus alpha. And in the case they are discussing for alpha between 0.5, and they showed this limiting object, so this Cauchy sequence, and it has a limit. The limit is going to be minus 2 alpha minus epsilon regularity. So that allowed them the starting point of why would they think the result would hold between alpha between 0.5. Now we have a cubic. Now we would think the cubic would be minus 3 alpha. Then I can start to do counting. Okay? But it turns out that's not quite so. It's not linearly decreasing in the same way. So what we proved in this paper, we just put onto an archive not long ago, a few weeks ago. We had the paper ready for over a year, and we're trying to polish up the proof. It took a long, long time to polish up. So anyway, now I think it's well written now, very clear. So what we did is we found out if you look at you see the cubic term, the weak product, so the weak polynomial applied to the lollipop, and the Duhamel operator applies to the weak product for all the three. We found that, so there is a critical value S alpha. For any S smaller than S alpha, we can find a value B0 greater than half, such that for such S and B, And the object we are really interested in is bounded in XSB. So that's a good news. Now let's see the S alpha, right? This is referring to this. We have this 1 here. Remember we had, so we have 1 minus 2 alpha, and for alpha between 0 and a quarter. When alpha between a quarter and 5/12, that's the only thing we can prove so far. And we get this critical value 5/4 minus 3 alpha. In fact, we don't know it's really critical. We started to have some inkling what the real critical value should be. But for the moment, that's the value we have. Now, let's consider the renormalization procedure. We have taken the un cube minus 3 sigma un. So that's the after the weaker renormalization. And so heuristically, in this business, you would write down the final equation as minus u3 plus 3 multiplied infinity. That's the variant block up, and that's the u, and plus this, right? This is meaning the above equation as n go to infinity, you have a limit. Now, again, by a solution, we mean there would be something of this form. To C would be limit n go to infinity of the linear part, some rough noise, which are going to be rough, and after n go to infinity. And V would be limited some remainder solution, and then your un above would be written down as Cn plus Vn. We take n go to infinity. So the two in the limit should have a nonlinear, the regularity should be separate. In particular, it's not quite unique because if you have something regular, you can throw into the rough part. But if you have something rough, you cannot put it into the regular part. This will become relevant. This is our result. It works, the range 0 to ace. That's where the stochastic symbols, that's the weak product for order 2 and order 3. In this case, we see that the regularity, so what we do is first we solve the linear equation with the noise, which we call the lollipop. And this stage, you write down the remainder equation. And the remainder equation turns out has a solution in the space a quad plus epsilon, a half plus delta. Let me remind you that this Bouguin space evolving with time. And at time 0, it has the regularity of quad plus epsilon. That's what where you have a solution for determinist case. So H, a quad plus epsilon, is classic. And we have we have our expansion, the remainder equation. We can solve, everything has a limit in the corrector. We can solve the remainder equation after proof the remainder equation. Inside the remainder equation, all the terms have a limit. So you have actually a limited object, and you can have solving that equation for V. Now, it turns out that, so this is all business as normal with normal counting for a quarter, for ace. But above ace, the normal counting doesn't work anymore. The reason is if you take the cherry and you multiply your remainder term, you would see this object is not well defined. That's the way. And that's not well defined in the limit. And so what one do in this circumstance is the following. We started to define a random operator, JV, So this is something we learned from the paper of Bringham. So instead of treating this as a product, it doesn't make sense. We treat this as linear operator. Okay. Now, if from V to the product by Cherry of V, that's you treat it as linear operator, we can prove that linear operator, the linear operator treated as a linear operator doesn't help, but it does help because when we want to look at the term of like this, we need to look at the apply Duhamel. Well, if the product doesn't make any sense, I cannot apply the Duhamel. But on the other hand, if we treat it as an operator, we can apply Duhamel to this object. So that's what happens. You're allowed to use the multilinear smooth effect. That's why we use a random operator. So that's the trick. So this stage, we have to treat it now already use this with random operator. Otherwise, we are on the same space. Now, at the different range, for alpha greater than a quarter, this linear operator, in this case, the linear operator goes from the correct Bougain space to itself, the quad plus epsilon, which is conformal to the determinist case result. Now, on this stage, the linear operator is in 2 alpha minus a quarter plus epsilon. So that's actually a smoother space than the one earlier. So now the linear operator goes from a smaller space to a small space. That means the remainder term had to live there. So the remainder term is very smooth now. So we have this result. But then if you go to 3/10, above 3/10, things changed again. The reason is that now this term, okay, this term normally in the first order expansion, we put it into V, okay? But in this case, this object, which is belong to this S alpha space, remember, xt S alpha, but the V needed to be in this space, and that one doesn't belong to this space, okay? It's not smooth anymore, you have to throw it out. Now you throw it away from the smooth part, you put it into the rough part. So how to do that? We have to add it as a symbol, solving linear equation iteratedly, now with the right-hand side given by this as one thing. But as a result, we have lots of stochastic symbols of this form. Well, this means triple product, multiply a lollipop and integrate over by the Duhamel and so on. We need to prove all of this has a limit, which is sort of a tedious work, I would say. Okay, so that's the remainder equation in the first order expansion when the triple product is sufficiently smooth, and then the V is going to be U minus the lollipop. So then there are 4 terms. The product, the triple product, we applied to Duhamel. We already know how to do it. The second term is where I say sometimes you look at the product and show it converge to something meaningful, or we have to treat it as a linear operator applied the Duhamel to the first term. At least that's a naive interpretation of the random tensor theory. And then there are a couple other terms. The Vn is nice, then your Vn squared, that's nonlinearity, and the Cherry is reasonably good. So that's the first order equation. Now, I think I already explained this part. How much time do I have? I guess 20 minutes, okay. So I already, thank you. I already explained this. I forgot I have these slides. So maybe I just, this is the one in the graph, and I recap it. For alpha in certain range, we expect V belong to the good, the space which we think it should belong to. And the product is well defined between the cherry and V as a distribution, because V is reasonably, the sum, the regularity is reasonably good. And then there is locally well-posedeness theory in this XT. For initial data, the initial data always is the same as this S part. For initial data is this. Now, plus that, the solution is stable with respect to the enhanced initial data. By enhanced initial data, we mean the initial data plus all the data parameter set, which means the lollipop and the cherry and this guy. Together, that's the initial data set. And the solution is stable on the, continuous with respect to these objects. Now, between 8 and 3/10, and this cannot be defined directly, so we explore the multilinear smoothing effect. Coming out of a dispersive cancellation means just you are doing all the free mode. When you're adding this free mode, the same mode together, you look at the product, you see lots of cancellations. So you explore that cancellation. So this allows to close, well, that's a part of it, allow to close the fixed point argument in this way. So now here's the proposition, which I explained already. So in two different range, we see this random operator defined as an operator applied to Duhamel. And this would be a linear operator, almost surely belongs to a linear space, goes from the Bourgain space with S equal to quarter plus epsilon, and delta equal to quarter plus delta. So you take that Bourgain space to itself. That's what this space is. For this range, it takes the same Bourgain space with S equal to 2 alpha minus quarter plus epsilon, delta B equal to half plus delta. It takes that Bourgain space to that Bourgain space. So as usual, to prove this, we use a lot of Kolmogorov theorem. We have to look at the piece moment of this object as a linear operator norm and compute it and prove they are finite. So again, it's just the result as in the graph. And I will explain the S alpha a bit more, and that seems very relevant. So now the main result is over. I will talk a bit of the proof discussion, the techniques. The one proof, so as I mentioned, the lollipop is in WS alpha, just a little bit below S alpha. S alpha is given here. When alpha is greater than 310, and this is too rough, and what we do is we write down the rough part being the lollipop plus this, we call it chicken foot. And so that's the triple product applied to Duhamel as well. Now, if you compute the remainder term by this formula, so the remainder is un minus these two terms. Now we have to expand the whole equation. You see it have now 9 terms in this. So this is the remainder equation. So the first task is to go through each object to see the product, all of this as limit n go to infinity. The Vn, not the Vn part, Vn you say there's a certain, we assume is in a certain space. Now we want to say when n go to infinity, all these stochastic terms make sense as limit go to infinity. And there's lots of them. I guess that's why probably people work on stochastic wave equation always write very long papers, because you have to prove each term has a limit in the correct place. So once we show that it has a limit, we have a limit equation. And that limit equation then is not difficult to prove the contraction argument works for that space and has a limit. So now I'll look at, so this is second order expansion again. So the theory is the following. You take U0, U1, that's your initial data. Now you throw in the initial data is the cherry, the random operator coming from the product, and the chicken food which comes in, which we also throw in the raw part. Then you look at all that terms. You look at them as independent data. So that's my initial data. Then you want to prove everything is stable with respect to this initial data. In the last regime, we also need additional random operators. So this object also considered as a random operator. Maybe I shouldn't use this one. And we need to prove their operator norm is also bounded. Okay, so maybe this is a formulation of the proper theorem. So, which does the first part is alpha between 0, 3 1/4, which tells us that they are, for all epsilon greater than epsilon 0, delta greater than delta 0, epsilon 0 and delta 0 to be determined. And there's a local well-posedeness and continuous theorem in this space. And that's the alpha in the second range. We want to, this is the important part also. This Bourgain space is continuously embedded as in time, is continuous in the Sobolev space, a quarter plus epsilon. I guess that's the saving grace. That's what we wanted. Okay? And same here. We are on the different space. Again, they belong to the continuous space here. Same as here. So these two sharing the same remainder equation, the last two sharing the same solution space. Okay, so here's some technique now, finally. One of the very important techniques which we struggled to understand, and in the beginning we didn't understand anything, and so Ren Xianfeng, he is very, very strong in all of this wave equation, Schrödinger equation. And he was reading lots of current literature. He said, there's lots of interpolation equation, looks correct, I don't know how to prove. I said, well, you can just go to ask them. He said, I asked afterwards. They said, it's common sense, a proof takes 100 pages, so nobody was going to prove it. So we struggled with this. Then we came up with a half-page proof for the basic principle. Use a complex interpolation method. So we wasn't sure which we use, a real or complex interpolation method. So the result is the following. Suppose you have, so we want interpretation between L2 and LQ and R. That we know how to do it, right? So in the between, we would have the usual Holder inequality that give you the middle point for that, if you want to do L2 space. If you want to do XSB space, so I want SB and to be connected to the 0, 0. And important thing, this is L2, okay? And then we want the middle ground, theta between 0 and 1. We want this guy. Now, the interpolation theorem says that the LT Q theta, LX R theta is actually embedded in XT as theta B theta. And that is the interpolation theorem. But the QRs are related. They have to be wave admissible. Remember some condition like this. And there's equality. I think there's inequality. So there's equality, there's inequality in the admissible pairs. So all of this should be admissible pairs with respect to the SB, with respect to S. Then the relation, the Q, if you want this one corresponding to that one, you have this relation, the QR solving that one. Now, that one was a relief to prove it, but that's not how you use it. So to use it, so essentially for XSB space, we have triple product. We have to bound the triple product for XSB space by each of them in the correct space. So if we do Holder, we know exactly how to do it. In SB, you see these relations, and that make nightmare to find the correct admissible pair to apply. So there's lots of work come into this. So whenever we need a trilinear estimate, we go to there and find an admissible pair, and Xianfeng did all the work. So here, for example, this is one example of many of the trilinear estimate we need. The triple in XT minus 3/4, minus half, and that's controlled with, we allow to get a bit of T out, and this U is in this Sobolev space, and the V and the W, we take the Bouguin space and quarter, and minus alpha minus epsilon. So the hard work is to find out which inequality we should be using, and how do we get it with all the correct exponent. So that's one example of it. Maybe I'm running out of time. I can wrap up. That's technicality. That's lots of them. So one of them is called when you have products, you have your white noise like this. Well, the beta n we can split it right down like this. Where W and 1 are independent, they are independent, you have some relations like that. So the technicality, one of them come in is you take the product. The product, what is it? Is the power 3 of a power, a series, a sum of a series, right? Now you have to add on all these frequencies. So you have N1, N2, N3. You add it together, EI, N1 plus N2 plus N3, and then you code N. So now you have the correct free mode for this one. And then these guys, you have to sum them up. Now, if you want to work on that, you want to apply Ito isometry, you see these products, and then you have to turn the product into a stochastic integral. Otherwise, how would you apply Ito isometry? So this one you apply Malleman calculus. But Malleman calculus cannot apply it at this level with two sets of this. Why? Because they usually applied for the same Wiener basis. So for that, we turned the integrals into a different Wiener integral. So that's Wiener integral of a sequence with respect to a Brownian motion is a sequence of Brownian motions. And then we can write down the second prototype as the Wiener integral, the complicated Wiener integral with respect to a tensor, and the third one with respect to tensor, the long form is this. But the point is, with this, we are allowed to use a product formula and all the correct isometry allow us to simplify a lot. So that, I guess, that's what I'm saying, that's the product formula we want to use. And that allows us to estimate XSP norm of integral of this form by some of the Fourier transformers with this guy. In the end, we could just compute all of them. And finally, when we do these computations, you take a summation, 3 indices in Z2, so you have n to the 6. You have to, it's not summable unless we have enough cancellation. So after you do turn everything into determinist estimate, do some correct bound and trilinear estimate, we would end up with n1 plus n2 plus n3 to the 2 power s minus 1. You have this guy, and you get nj to minus 2 plus 4. And then what you do is when you do summation, we take the phase function, we truncate the frequency into little wood Paley block. So we take a block of size between n over 2 and n, and then we take a frequency in that block, and then we look at in this ring, we do each estimate. And once we've done this estimate, it becomes a counting estimate. So most of the nightmare is the counting estimate. I think I'm done. Thank you very much for listening. I don't know.
This linear operator.
Which one?
This
J, yeah, this one. Yeah, yeah.
So is the idea when you combine this with the dual operator that you can exchange the order, or how?
Essentially, that's, I think naively that's the idea, yeah. Okay. Because you cannot apply it directly, but as the operator, you don't have to put it in. You can apply the object.
Thank you.
Yeah.
Okay.
Essentially, there's another layer of something's happening there. Yeah. So that's what they call the random tensor, and it just is a random linear operator, bounded linear operator.
Okay. The combination of Duhamel and this is a random nonlinear operator.
So this is what in the field called a random tensor. Yeah.
Okay. Thanks.
Okay. Are there some other comments or questions? Oops.
So I wanted to ask about the sign of the nonlinearity. So this local well-posedeness result, I mean, whether you have a minus or a plus in front of the cube, is it the same or?
Oh, I think the plus minus, what? Oh, did I?
Whether it's focusing or defocusing.
Yeah, I think I'm using minus U3, but the plus minus sign for us, I don't think it made a difference.
But I mean, from the point of view, if you want to try to extend it to a global well-posedeness result.
Yes, like that would be. Yeah, that would be relevant, and we don't have a result.
Ah, okay, you don't.
No.
You don't know.
Yeah.
Okay.
Yeah, it would be nice to have it, and that's Xianfeng's ambition for the something.
Yeah.
If you want to talk, that's to him.
Okay, thanks.
Merci beaucoup. If you multiply the Laplacian operator by a positive parameter, how does it affect the solution?
Could you say it again? Apply the Laplacian to?
By a positive parameter. Only the Laplacian.
Only the Laplacian to, oh, I see. You want me to apply this to?
Yes, by a positive parameter.
Yeah.
No. Multiply. Just multiply.
Like times by 10. 10 times the Laplacian.
Oh, I see.
Yeah.
I guess it's not going to make much difference. Well, you know, you have. Let's see. I think it doesn't make a difference in terms of local well-posedness. What are you saying?
No, I agree.
Yeah, you agree. Okay. You're shaking your hand. I thought I thought you were shaking your head to me. Yeah. No, because that's in terms of technical level. You see, the operator Laplacian on the torus, right? The trigonometric functions. They are the eigenvectors. You get 0, 1. So you get basically n squared as it is. So what we did is take a Laplacian, 1 minus Laplacian. Laplacian is negative, which one? Laplacian is minus Laplacian is positive, lifted to 1. If you have a tan or anything, because the bottom spectrum is 0, it doesn't change anything if you just multiply it in terms of the analysis. But not at this level, though. Yeah.
Okay, let's thank again the speaker and postpone other questions to the coffee break.